Hello students, welcome to EPG Pathshala. I am Dr. Anjali Sharma from University of Delhi. Today we are going to talk on module Colloidal Synthesis of Quantum Dots under the paper Physics at Nanoscience and Technology Part 1. So after completing this module, the students will be able to understand what are quantum dots, what are the colloidal quantum dot systems, miscellaneous synthesis of colloidal quantum dots, high temperature colloidal synthesis of A3B5 semiconductor quantum dots. Quantum dots have been studied for approximately 2 decades with view towards the aforementioned applications as well as for the pure science aspects concerned with the physical, electronic and non-linear optical properties that lie between the molecular and the bulk. While quantum dots have dimensions that are on the order of nanometers, they still contain hundreds to thousands of atoms. Most of the quantum dots that have been studied to the date are dispersed in the host matrix such as glass or a crystalline counterpart. The newest research is often being carried out using colloidal quantum dots that may be placed on a substrate in a self-assembly process to produce films, patterns, and wires. A capping structure is used in colloidal quantum dots to charge, passivate the surface and the defects. Capping structures act as an interface between the quantum dots and their surroundings. With appropriate capping, quantum dots can be used in sensors or integrated with biological systems. For these reasons, an investigation into how to make cadmium selenide quantum dots with varied capping structures, particularly how to make the robust zinc selenide capped cadmium selenide variety for biological marker or polymer microsphere tagging application is of interest. The use of TOPO, stearic acid, DA and phenylsulfone, aminophenylsulfone and other organic molecules as the capping structures of cadmium selenide quantum dots needs to investigated during their initial production of the nanoparticles. The advantages of a colloidal system over a matrix or quantum dot system are many and varied. Three-dimensional interaction of quantum dots with their surroundings is desirable as it allows for applications such as tagging of DNA or aqueous monitoring for biological and chemical changes in a given environment. The colloidal system allows greater available surface area and environmental contact than the matrix or quantum dot or substrate or quantum dot system. The colloidal system also provides the ability to change the solvent surrounding the quantum dots, deposit the dots through precipitation onto a substrate, or diffuse them into a polymer. Such flexibility makes bulk manufacturing of quantum dots desirable. Quantum dots are being produced at the laboratory scale out of a variety of materials in accordance with the properties desired. The colloidal quantum dot system. Colloidal processing is liquid phase condensation, wherein chemical reaction supersaturate the precursors and cause nucleation as well as growth of nanoparticles. Post-synthesis treatments are very crucial for applications of these quantum dots because the as-synthesized quantum dots have poor quantum yields for luminescence. Additionally, it is presently not possible to synthesize nanoparticles with efficient luminescence by other techniques. We will now discuss the most frequently used physical method for post-synthesis treatments of quantum dots. Because the freshly prepared quantum dots are synthesized by very low quantum yield of luminescence, micellar synthesis of colloidal quantum dots, water in oil, a reverse microemulsion technique to prepare colloidal quantum dots was first proposed in the last 2 decades of the 20th century. The technique involves a chemical reaction which can be controlled by intermicellar exchange of reactants, resulting in nucleation and growth of nanoparticles. This process has been employed to produce a variety of nanoparticles from different substances such as metal, metallic oxides, silver halides, and semiconductors. Earlier, nanoparticle growth via reverse microemulsions was assumed to be limited by reverse missile shells. A reverse missile shells are monodisperse. The nanoparticles thus produced should be monodispersed. Based on this logic, the size of nanoparticles could be altered since the size of reverse missiles is controllable by variation in the concentration of water and surfactants. So students, now let us see the high temperature colloidal synthesis of quantum dots. Murray, Norris and Vivendi were the first to report colloidal preparations at elevated temperature. They had produced colloidal quantum dots of cadmium selenide, cadmium sulfide and cadmium telluride having adjustable luminescence via a one-step process, which is called as pyrolysis of organometallic precursors at 300 degrees Celsius. The process involved injecting cold precursors, a mixture of TOP selenide and dimethyl cadmium in tri and octyl phosphine in hot trioctyl phosphine oxide. This resulted in abrupt nucleation and a subsequent decrease in temperature of mixture about 180 degrees Celsius. After this point, nucleation is stopped. Then the temperature of reaction mixture was slowly increased to 230 to 260 degrees Celsius. the temperature was maintained at this value during the nanoparticle growth. Nanoparticle synthesis at such high temperatures cause annealing of the produced particles, thereby producing defect-free crystals. Thus, prepared colloidal quantum dots exhibit strong band-to-band fluorescence. However, luminescence from deep traps could not be seen. The colloidal quantum dots or CQDs produced by this method are of high quality, that is, temporal separation of nucleation and growth processes. Second, the produced nanoparticles are annealed. And third, the elevated temperature synthesis produces defect-free quantum dots having high quantum yields of fluorescence. Another method for the fabrication of quantum dots is high temperature colloidal synthesis of A3B5 semiconductor quantum dots. Cadmium selenide or CDSE quantum dots have impressive properties. However, their use is limited owing to their high toxicity, cadmium being a carcinogen. Therefore, alternative methods have been developed to coat cadmium selenide quantum dots in order to reduce the toxic effects. Examples include silicon dioxide or amphiphilic polymer. The coating of these shells decrease the amount of cadmium ions escaping from the nanoparticle cores. These compounds are still toxic and remain unsafe for use. Less toxic and cadmium-free alternatives such as A3B5 semiconductors have gained huge attention these days. For example, gallium arsenide, indium phosphide, indium arsenide, and indium phosphide matches cadmium selenide in terms of physiochemical behavior and is the potential candidate to replace cadmium selenide. Indium phosphide is a direct bandgap semiconductor and has a bandgap of 1.27 electron volt. For comparison, cadmium selenide has a bandgap of 1.74 electron volt. Indium phosphide has tetrahedral structure of Wurtzite type. Since contribution of ionic bonding is 15%, covalent bonding predominates the crystal structure. The predominance of covalent bonding increases the excited Bohr radius to about 10.6 nm, which is much larger than that of cadmium selenide, which is 5.2 nm. Thus, size effects are more pronounced in indium phosphide in comparison to cadmium selenide. Furthermore, strong covalent bonding enhances the photostability of indium phosphide quantum dots. Thus, These quantum dots can be used as a substitute to cadmium selenide quantum dots in applications such as in biomedicine. Even though indium phosphide quantum dots offer better properties than cadmium selenide quantum dots, indium phosphide quantum dots have not been synthesized similar to cadmium selenide. The elevated temperature synthesis under conditions, solvent precursor, etc., similar to cadmium selenide have not produced indium phosphide satisfactorily. The reaction rate of nucleation and nanoparticle growth are very slow, and production of nanoparticles of specific dimensions requires long time durations, sometimes hundreds of hours. Additionally, it is very difficult to get monodisperse quantum dots. This is because, owing to the strong covalent bonds, it becomes difficult to separate the nucleation and growth of nanoparticles. This results in a broad size distribution of synthesized nanoparticles, which in turn results in broad luminescence bands, namely full width at half maximum. FWHM is greater than 60 nanometers for indium phosphide, while it is 30 nanometer in cadmium selenide. Consequently, several synthesis routes have been developed to prepare indium phosphide quantum dots. The use of octadecene as solvent and fatty acids such as palmitic acid as indium coordinating ligand has caused considerable reduction in the synthesis time duration. The use of these reagents have also helped in producing nanoparticles having nano-size distribution of about 4.7% variance in few hours. Also, precursors such as indium carboxylates promote the synthesis of indium phosphide quantum dots. The choice of precursor has great influence on size of the synthesized nanoparticles. The reactivity of indium carboxylates and synthesized rates can be enhanced by using fatty amines as activating agents. The different sized indium phosphide quantum dots can be produced having tunable spectrum 390 to 720 nanometer within 1 hour. Phosphorus source is also important for synthesizing indium phosphide quantum dots. Mostly used precursors such as trimethyl salicyl trisphosphine cannot be used to grow bigger nanoparticles, since it is highly reactive, due to which it is consumed in a very short time after introducing into the reaction chamber. In this case, the nucleation as well as the growth of nanoparticles occur almost simultaneously, thereby precluding any possibility of achieving monodisperse phase. In addition to this precursor is very expensive, hazardous, and spontaneously inflammable material. Therefore, any large-scale production of indium phosphide quantum dots requires development of either alternate precursor or efficient synthesis techniques. To end, alternate sources of phosphorus have been explored. These include yellow phosphorus, gaseous phosphorus, pH3. pH3 is produced by the reaction of calcium phosphide, that is Ca3P2, or zinc phosphide, that is Zn3P2, with HCl. Tris dimethyl aminophosphine is another less expensive precursor for phosphorus, which is relatively safer to use. Tris dimethyl aminophosphine was used for the first time by Matsumoto and Yamaguchi and Song to produce indium phosphide quantum dots at elevated temperatures and having narrow size distribution. Luminescence spectrum for these dots was tunable between 500 to 600 nanometers by simply adjusting the synthesis time only. The growth of zinc sulfide shells on indium phosphide cores increased the quantum yield of luminescence from 1% to more than 40%. This core shell structure also improved the air stability of the quantum dots. There have been numerous efforts to prepare different core shell architectures by used various semiconductor shells like cadmium selenide, cadmium sulfide, zinc selenide, zinc sulfide, or zinc cadmium selenide, out of which zinc sulfide based quantum dots have demonstrated the best performance. The semiconductor shells can either be produced after the synthesis process or during the synthesis process of the indium phosphide quantum dots. Chemical annealing is followed by growth of wide bandgap semiconductor shell is an attractive mean, but chemical annealing of indium phosphide core may be deteriorate the structure of zinc sulfide shells. This may happen because HF blocks the surface of indium phosphide colloidal quantum dots. Zinc sulfide shells over indium phosphide enhance the quantum yield of luminescence. Additionally, the formation of indium phosphide quantum dots in presence of zinc ions reduce the surface defects and facilitates the synthesis of zinc sulfide shells. Further, zinc ions also increase the stability of the quantum dot surface. This has been attributed to the presence of covalent bond which form several deep surface traps or unsaturated bonds and packing defects in the indium phosphide quantum dots. The activation energies to overcome these traps are more than that in A to B6 semiconductors. By proper selection of these semiconductors having wide band gap to modify the quantum dot surface, it is possible to increase the quantum yield of photoluminescence. For instance, HF or NH4F treated chemically annealed colloidal quantum dots demonstration intense band-to-band luminescence. In this case, the quantum yield of luminescence was found to be increased by more than 30%. Indium phosphide colloidal quantum dots, when dispersed in tetrahydrofurane, exhibited stable and bright luminescence over 2 weeks. This is attributed to the occupation of phosphorus vacancies by fluoride anions during chemical annealing. This resulted in the removal of oxygen from the oxide layer. In another technique, chemical and photochemical annealing processes can be combined. Thus, a further UV illumination for about 8 hours almost doubled the quantum efficiency. Additionally, covering the indium phosphide surface by a wide bandgap semiconductor is an effective method to enhance the quantum yield of the indium phosphide quantum dots. So students, let us now summarize what we have learnt in this module. We have learned what are the quantum dots. We have also understood the colloidal quantum dot system and studied the micellar synthesis of colloidal quantum dots and high temperature synthesis of these quantum dots, and also the high temperature colloidal synthesis of A3B5 semiconductor quantum dots. Thank you.